My name is Leonard Xu. I'm the Flink CDC team leader at Alibaba Cloud, and I'm also Flink committer and PMC member. I've contributed to Flink SQL and Flink connectors more than 5 years. And recently I lead the Flink CDC project in past 3 years. Today my session topic is about deep dive into Flink CDC, addressing streaming ETL pipeline challenges. Okay, my session consists of 4 parts. The first part is the overview of Flink CDC project. Second part is some internals of Flink CDC. And then I will talk about best practice of Flink CDC YAML. And at the last section, I'd like to share the community status and our future plan. Okay, let's start the first part of Flink CDC overview. What is Flink CDC? Some of you may have heard of Flink CDC project yet. Flink CDC is a streaming data integration tool that implements unified snapshot reading and incremental reading based on the CDC technology of database logs. And when combined with Flink's excellent capability and rich upstream and downstream ecosystems, Flink CDC can achieve real-time integration of massive data. Just as the diagram shows, Flink CDC will read the data snapshot from your database table and then automatically switch to read a change log from your MySQL or Postgres database. And then the upstream operators of Flink or upstream systems will receive real-time data, and the real-time data can be looked at as a real-time consistent snapshot of your upstream MySQL or Postgres table. Look at the traditional data integration pipeline without Flink CDC. We usually need to consider 2 kinds of infrastructures. First, we need to do snapshot sync per day or per hour using infrastructure like Scoop or DataX. And we also need to do real-time sync to sync your change log using infrastructure like dbThermo or Clio. Finally, we will merge the snapshot table and the increment table per day, per hour to get the final merged table. But in this legacy we call the Lambda pipeline, we need to take care of too many infrastructures. And the data consistency and the data freshness is not so good. As a developer, you also need to care more data stack, like you need to know how to deploy a Scoop or DataX job, and you need to deploy dbThermo or Kafka connector cluster. But with Flink CDC, what we need is only a Flink job to build your data integration pipeline. Give an example about sync data from MySQL to data warehouse like Doris or Starbucks. We can define a MySQL CDC source to read snapshot data from MySQL database table and then automatically switch to read MySQL battery log. The Flink CDC makes the data integration pipeline more easy. So how we use Flink CDC? The classic usages including data sync, like move data from one place to another place. And Flink CDC can also be used in Flink SQL or Flink data stream jar job as a source connector. Of course, you can also use Flink CDC to finish your data distribution, for example, from MySQL to other message queue and to other data warehouse. And from data warehouse perspective, you can integrate all data together from external system. About the Flink CDC project milestones, we released the first version of Flink CDC in 2020 and released the 20.0 version in 2021. And we released the 3.0 version in 2023. After that, we donated the project from Vertica to Apache Flink community. In this month, we just released the latest 3.2 version. Okay, we just talked about Flink CDC's key milestones. In Flink CDC 1.x version, Flink CDC is just a set of CDC connector of Apache Flink. It can be used to simplify your data ingestion infrastructures. Compared with legacy ETL pipelines, with Flink CDC connectors, you do not need DB-thermal or Clio cluster anymore, as well as some message queue like Kafka or Parser. The Flink source operator of MySQL, just like the picture show, will directly read the data from MySQL database by running log-based CDC library like DB-thermal or Clio. In Flink CDC 1.x versions, we offer both SQL API and data stream API for all CDC connectors, like MySQL, PostgreSQL, MongoDB, TiDB, and so on. That means you can leverage Flink's SQL API and data stream API to write more custom logic after the data is captured by Flink CDC source operator. And for all downstream of Flink's connector, we can write changelog data to these downstream connectors. Flink CDC is pretty popular, but we also meet database lock scale-up issues in our production. So we proposed the incremental snapshot algorithm in MySQL CDC to resolve these issues since Flink CDC 2.0 version. The right part of this slide describes how it works. We will split a MySQL table to many chunks according to table's primary key, and then we will assign this chunk to readers. The reader will read the data that belongs to this chunk using JDBC query, and all chunk table schema information will be stored in the source operator state. About the state information, we also keep how many chunks the source operator has been read, and we can then restore from the checkpoint from this chunk we had read before the failover. We can do distributed scan during the large-scale snapshot with this incremental snapshot framework. And we also offer exact nuance semantics without locking your upstream database. We can support failover both in snapshot reading and changelog reading. Okay, in 2023, there are two important milestones for Flink CDC project. The first one is we donated Flink CDC project from Vertica to Apache Flink community. Flink CDC becomes the most active sub-project of Apache Flink community. Another one is that we changed the project operation from a CDC source connector to an end-to-end streaming data integration tool. We aim to build the best data integration tool in the streaming world, which offers the most powerful features, but with simple user interface. Finally, we decided to use YAML language to define the pipeline, which can gently support key features like schema evolution, entire database table sync, and transformation like projection and filter. So in the second part, I will introduce the internals of Flink CDC. When I designed CDC YAML, I realized the two key points from user's perspective. The first one is that users don't care how to implement a data pipeline. User doesn't need to care these technical details. And the second one is that user cares what they need. User only need to describe their requirements. This is the overall design of Flink CDC YAML. On the top of this stack is the key features user want. For example, like streaming pipeline, change data capture, schema evolution, schema inference, and sharding table sync. In the CDC connector layer, we offer different pipelines and different pipeline sync to support this key feature. And for users, you just need to write a YAML file, and then you can call only one line shell command to submit your YAML file to Flink cluster. The Flink CDC composer works like Flink table planner. If you are familiar with Flink SQL, it is used to optimize your job graph. It will produce a cost-based job graph from your pipeline. In Flink runtime layer, we offer some necessary Flink runtime operator so that we can achieve these key features like schema evolution and transformation. This is a basic CDC YAML example. YAML is pretty friendly to both users and machines. Simple API means for data integration user, it's critical important. User just need to specify the data source and destination with optional routing rule and transformations. We hope Flink expert is not required anymore in data integration pipelines. So for submitting a Flink CDC job, user can build a CDC pipeline by executing only one line simple shell command. The CDC composer will connect the source sync and other optional CDC runtime operators, create a Flink job graph, and then submit the job graph to Flink cluster. About the connector API design for Flink CDC YAML pipeline, you can see the Flink source provider and Flink source function provider at the bottom of this slide. Because we consider reusing the existing Flink connector API like source and source function to reduce our development cost. And the metadata accessor and metadata applier are designed to process schema change event. Besides the interface, we also consider introduce new data structure for better performance consideration. The normal data structure contractor in a data pipeline usually require both schema information and data information. And some advanced CDC projects may use schema-less data structure. They introduce a versioned schema ID just like Aerial format. In this way, we can save the memory usage because we use a single schema ID to represent an entire schema. But is this enough? The answer is no. We finally introduced binary data structure with the schemaless way. This design uses binary data structure to save more memory usage and only send schema when necessary. So when we should send the schema change event in the stream of Flink CDC, the event stream in Flink CDC including data change event and schema change event. We follow three contracts. The first one, stream will start with create a table describing the initial schema. Second one, all following data change event will respect this schema. At the last, a new schema change event should be emitted. Only the upstream system happens schema change. This design is friendly for memory and CPU usage. Why CPU? Maybe you will ask why CPU is related. Because with the next data structure use, we can save the serialization and deserialization of a record. The cost will decrease when we introduce the binary data structure. Okay, let's look into the most complex but also most attractive feature, schema involution. The schema involution is pretty hard to make it clear in a short time. I will briefly introduce the feature. The schema change event will be sent firstly like create a table. And the schema registry has a state machine to make the schema involution process works well. Firstly, when a schema operator receives the schema change event from a source operator, the schema operator will register the schema change and then write the response. And at the same time, all schema operator will hold upstream. No data change event will be sent to downstream. This request will be blocked if schema registry is busy, because the schema registry is a global coordinator. He will judge who should be passed, which request should be response and which request should be blocked. Once the schema registry accepts this schema change request, it will reject following schema change requests. Schema operator will broadcast the flash event. The flash event is used to flash all in-flight data, because the in-flight data may use old schema. So we need to flash this in-flight data firstly. After that, sync operator will notify flash in-flight is finished or not. Schema registry will apply schema change once the flash finished. Usually, the schema registry will call the sync operator to execute a DDL, like create a table in downstream system, or execute a DDL to add a column in downstream system. And at the end of a schema involution process, schema registry will confirm this round of schema involution is finished or not, and change its state to idle. After schema registry confirms the schema involution finished, its state will become to idle and ready for next schema involution request. In fact, when we deep into schema involution use case more, we realized that we need a different mode for different pipeline and for different use cases. So recently, we introduced a different schema evolution behavior mode to make a schema evolution feature can be production ready. The default lenient mode is recommended. It keeps all data as much as possible, and it can recover job even in some color case, like concurrent schema evolution happens. The ignore mode will ignore all schema changes and keep the original schema. It works like your Flink circle job. The try involve mode will try to apply schema firstly and then fall back to cast data change event as much as possible when error happens. The involve mode will apply schema firstly and then fail the job directly when any errors happen. And the exception mode just reject any schema changes when we detect schema change happens in upstream database. The last internal of Flink CDC I want to share is about transform. There are also too many technical detail I can share, but I plan to simply introduce it for the speaking time consideration. For CDC YAML support, Flink CDC YAML supports projection, filter, and UDF in transform. It's pretty easy to learn as it is SQL-like style. So by the way, the transform can work with schema evolution feature. So it is possible for your case, you want to project some existing table columns and keep new added column or rename existing column in the future. Okay, in the best practice part, I will show you some use case and Flink CDC YAML how to resolve this use case. The first use case is that when user want to sync all tables from one database to warehouse, and he or she hopes that once the table schema changes in MySQL, the table schema in downstream warehouse like Doris will change automatically. In this case, you just write a simple YAML, just like the left part of this slide. The downstream database contains 3 tables, and any table schema changed, the downstream table will change it in real-time style. For example, the table orders in downstream Doris database will add a new column amount once upstream MySQL table orders schema changed, because upstream MySQL table orders add a new column amount. And then they will write the latest data with ID 3 and with the new added column amount. The second use case is some huge business may use sharded table, but user want to merge all data of table from sharded table or even sharded database to one table in their warehouse. In this use case, we can use a routing rule to control the destination of the data. In this case, you just need to write a YAML file with an optional routing rule. The source table supports rejects pattern. That means it will match multiple tables like table user 01, 02, and 03. And in the destination of your Doris, you can only see one table users. The last use case is that user want to do some transformation, like they want to do column projection and filter with given conditions. In this use case, you can write a SQL-like projection expression and filter expression in your YAML file. It's pretty easy if you have write any SQL job before. Okay, Flink CDC is an open source project from the day one. The last part I want to share the community status and our future plan. Flink CDC now is a sub-project of Flink community. We follow single contribution steps, mailing list, issue management with Apache Flink. And now we have more than 100 contributors and more than 1,000 commits and more than 5,000 GitHub stars. Compared with the metric of 2023, the community is becoming more and more active. And also welcome to join Flink CDC project and the Flink community. About the future plan of Flink CDC project, we will focus on expanding the ecosystem of Flink CDC, especially support more external systems in Flink CDC YAML pipeline. And we also have a plan to support batch pipeline because we currently only support streaming pipeline. We plan to support batch pipeline next. And we also have a plan to support AI model in transformation. On the other hand, I think the production stability is pretty important for data pipeline. So we also have a plan to improve our production stability and also the version compatibility with Flink, because we have supported many Flink minor versions. Okay, that's all of my session. Thank you.